everyone. My name is George Porter, and I'm a professor at UC San Diego, and it's my pleasure to moderate this panel discussion. So this is going to be kind of an open discussion where our keynote speakers are going to be able to talk and discuss amongst themselves and answer questions. You've already been introduced to Elaine, Elaine, Karen, and George Papin. And Dan Kilper from Trinity College Dublin is going to be joining us for the panel discussion here. Now, I have a couple of questions that were sort of put together in advance. However, I think that to make this more interactive, if you have thoughts, questions, you want to follow up on topics, especially topics that cross the expertise of the four panelists, please feel free to raise your hand and ask those questions, and we'll address that to the panelists. Okay, great. So I will start off though, just to kind of seed the discussion by posing this larger question about one of the goals of this HotOptics workshop, which is really to try to connect the optics and networking community. It's here at SIGCOMM. Part of that is to try to drive that collaboration home. And so, you know, one question has to do with sort of what has been your experience working across that boundary, and are there any things that you think would help facilitate those kind of collaborations or discussions? And perhaps I'll ask Elaine to kick off the discussion.
Thank you very much, George. Just thinking back, I did my PhD looking at optical subsystems, so physical layer, and then after that to layer 2, back and forth. I think one of the benefits of working and straddling across those two areas is the awareness of the limitations on both. When you're working on optical networking, you understand the physical limitations of components, and likewise, when you're working, for example, with a VCSEL and you're looking at link budget, you sort of understand the sort of the pitfalls and the challenges that you have to look out for. As to your question, as to how to foster collaborations, I think something like this, workshops, forums, and something that I'm really, really envious of, my colleagues and fellow researchers in Europe and US are consortiums. For example, Horizon 2020 previously. Just trying to get involved with large grant and funding applications, something that we don't actually have in Australia, and so I will have to take so it's my own initiative to attend conferences, to talk to people, to keep in touch, and to be visible. But if you're in a situation or you're in a group that readily have that sorts of opportunity, I would say, and especially if you're a PhD student, sort of put up your hand and, sort of volunteer to help, write a grant, or to organize a workshop, organize conferences, and also put up your hand to sort of review papers. I think, very early on in my PhD career, I've done a lot of reviews, and actually talking about paper review, Karen gave me my first job as an editor, associate editor at JON. And so that came up from, the visibility, the sort of networking from being at conferences. Yeah. So that would be my sort of 2 cents as to how to sort of foster those collaborations. Yeah.
Okay. You, George?
So I have had the benefit of actually, for now, going on 15 years, working with systems people almost every day. And good news and bad news in the same statement is that systems function by proper abstractions. And a good abstraction is absolutely essential for systems research, because if you can't abstract, you can't deal with all the complexities of the systems that we deal with. It's just not possible, right? You can't worry about the polarization of a photon and like a congestion control in the same sentence. But at the same time, a proper abstraction is a very difficult thing to get right, because while we try to abstract away some of maybe the extraneous things in the physical layer. Unfortunately, many of those things come back to haunt us when we don't do a proper abstraction. So I guess for the systems people here, that's a really hard thing to do. Is getting the right abstraction is essential, but it's actually really hard. And I think that's what we've learned over the years.
So, yeah, I'll say that early in my career as a PhD student, let's say, I grew up with this idea that optics was going to take over the world and replace electronics. We were going to have optical computers and all optical regeneration and optical packet switching and everything. And then I went to Bell Labs and I discovered that it was all a hoax and it's not really going to happen that way. Actually, and then I started to learn that there's this really interesting interplay between the electronics and the optics, and actually it's much more subtle than that original view that I had, and came to appreciate that over time that's much more interesting. But still, we have these somewhat siloed communities, and that's where these ideas come up about that optics is going to take over everything because it's coming from this optics community that's not talking with the data and electronics networking community. And so we really get a lot of value then, I think, from understanding what's going on in these different communities, and we need that. On the other hand, having then tried to work across that boundary, what you discover is that this kind of interdisciplinary research, while everyone says it's a good thing, it's not good if you're an assistant professor, let's say, or you're trying to do something early in your career, because at the end of the day, interdisciplinary papers often get judged poorly because you're an optics person, you're publishing in a data networking conference, you don't speak the same language, you don't express things in the way that they expect, or the other way around, data networking person, you try to get a paper in OFC or something, and people at OFC look at this person, what are they talking about? They don't really understand, and it's really hard to work across those boundaries. And so, but we need to do it, and we need to encourage it, and so it's something that we need to work at, and I hope that events like this will help us to cross those barriers.
Yeah, it's really intriguing to see everything that was said so far, and I have to say I agree with much of everything that my co-panelists said. I've also been working at the intersection, for almost my entire career, and to add to that, I would say two things. One is, looking at things from the physical layer to the system layer and back down again is, it's very rewarding because you get to, ultimately the question is about what kind of impact you can have, right? And if we look at from the system level and think about, things like performance or, execution time or energy consumption, that really drives the most interesting questions, in my opinion, at the physical layer. And so working at this intersection can lead to very impactful work. And you can look at, as Dan said, the folks on the optics community that will come up, and I like to give the example of, here's the fastest modulator in the world, right? Let's say you came up with a, 400 gigahertz modulator, right? Very hard to do. The question from the system level is like, what good is it, right? How would you actually use it? And it's not going to be the most energy efficient. It's not going to be a good interface to the parallel electronics, and so on and so on. So I think it's a really rewarding area, and being able to go back and forth is really key. Unfortunately, you have to learn both sides, right? And it's more challenging and takes more time, but I think it's some of the most rewarding things. The second part is a little bit more practical. I think that I'm also an experimentalist, and so to do work at the systems level requires, it's a bigger challenge. And there's some examples you can use commercial components. You have to also design your own, and so you have to also think about the physical layer from start to finish, not just here's one new device that I'm gonna write a paper on, but here's, you know, how I integrate the device, here's how I package it, here's how I can actually integrate it into a system. So those are really exciting challenges. And lastly, I would say workshops like this are really fantastic in terms of bringing, you know, the communities together. This has been a fantastic workshop today. I really appreciate for the organizers. I hope you can build on it and keep it going. I look forward to more.
Okay, great.
I'd like to ask Yiting actually one question. You said very early on, the first things you said in today's workshop is that this is one of many. So is HotOptics going to be?
Well, we hope it can continue.
Is there anything we can do to, you know,
Yeah,
sort of
definitely.
motivate?
Well,
with the
by showing up, giving
Yeah.
talks, giving panels, I think you guys have contributed a lot. So we hope this will continue. We'll probably send out surveys. You guys can send us some comments. What do you think can be improved next year? And if it goes well, maybe we can enhance marketing. Well, we started a little bit late this year. Yeah, and if we can attract more submissions, that would be great. Yeah, hopefully this will turn into a real workshop like HotNet.
Sorry, George.
Oh, no, not at all. Like I said, I want this to be interactive, so if anyone in the sort of audience here has any particular questions, feel free to jump in with them. Maybe while you're sort of thinking of a couple, I'll just throw one out there. So all of you are very active in research. You've experienced having to kind of focus your attention in a particular area. If you kind of up-level, if you could wave a magic wand and get either the optics and photonics communities or the SIGCOMM community, data communication community, whatever that community is, to focus on something you think is important that they're not working on, what is something that you might pick? What is something that you think is urgent that could use more thought that is maybe being underserved right now based on what folks are working on? Yes.
I can say something. I guess coming from the bottom up, which is, I feel more comfortable at the hardware level, photonics level. We always struggle to connect with, how would you map the workloads, the applications, the algorithms onto a photonic architecture, and that interaction between the physical layer and the higher layer, I think is difficult. And I'd love for the networking community, whatever we want to call it, to be able to start exploring what if we have uniform bandwidth across the system, right? Which we don't today, right? It's hierarchical. We design things to be locally processed. What if we could open it up? What would that look like? So that would be a wish.
So maybe hollow core fiber. It's going to be big. Right? I didn't hear it mentioned today, and with Microsoft purchasing, was it the Mensa, the Southampton guys? I guess I'm convinced now that it'd be interesting to see how it moves in and displaces single mode fiber, and how that'll evolve over time. I experienced single mode displacing multi-mode. It seemed like it took forever to get all that multi-mode out of there, but I think we're going to see the same thing happen with hollow core fiber, and we need to rethink networks and how they optical networks and how they interact with computer networks in the hollow core fiber regime.
So we were having a discussion earlier on. I think this may be true of all device and systems groups, but I think it's particularly true in optics that we kind of have this gap, is that we've had a lot of papers that take research devices on and argue system level concepts on a very small scale. And by small scale, I say less than 10, okay? Maybe even as small as 4. And that's absolutely essential, because you have to be able to take research devices and show some level of system functionality. But on the other side, of course, to truly have impact, you have to show something of a practical scale. And my admonishment to the younger people today about don't spend 6 years developing a system, we were fortunate that we were already tenured at that point and really didn't care. But there has to be some way of bridging that, right? The problem with academic research is that from an industrial perspective, they can't tell what a 4-node system really will do at scale, right? And the question I think for all of us is, how do you do that, right? I mean, we were fortunate that we built a 128 port switch, and that's a big switch for academic institution. But I wouldn't recommend it, and as we were kidding around, I definitely wouldn't recommend it starting out your career. All right, so we have this kind of, from an academic perspective, we build these kind of small scale systems to kind of, and then we kind of, you know, let's say optimistically extrapolate the performance at scale, right? And from another perspective, the people who are actually building systems don't know if these things are actually going to be production, if they can actually work. So we have this kind of gap, particularly from an academic perspective, and I'm not sure how to fill it in. I'm really not, because you know, to Dan's point, the academic reward system really doesn't reward it, right? And it's a lot of very nitty-gritty engineering detail that has to be managed. And I'll be honest with you, I don't know the answer to that, right? But I do think that if someone asked me a key question of how we move fundamental device work like what Karen does and try to push it so it's more rapidly adopted, right? That people believe that we can take some of this novel device technology and really build practical systems out of it. That would be a really good roadmap. That would be something, you know, whatever you want to call it, incubator or whatever, that we actually build systems at a practical scale, right? And the best example I can give you is a very famous example out of DARPA. Were you involved with Monet?
No.
Okay.
I was a little bit.
Yeah, okay. So DARPA has this extremely famous program where they just spent a ton of money and took fundamental research devices and built a large-scale system out of them, okay? And I would say that things like that, Monet was the first wavelength switched, was the first big wavelength WDM system.
How long ago was that?
Early 90s? Yeah, early 90s. But it had huge impact, enormous impact. I mean, it literally pushed the field. There was another very large program on the VCSEL. So the VCSELs were research devices at one point, and they just hammered on them and said, let's make whatever, some ungodly number of wafers to find out what these things would look like at scale. But something like that, I think we need to do, because first of all, it's much more complex, unfortunately. That's 30 years ago. So trying to do that now is going to be much harder. But I think we almost have to do it because right now the pipeline of trying to get new stuff out into systems, I think is actually taking longer, not shorter. It's harder to get stuff out.
In interest of creating some controversy on the panel, not
Okay,
really
let's talk about
controversy,
it.
but I'll push back on some of what you said, George. You know, I think that there are different back pressures to inserting new technologies into systems. I think on the switching side, there's a lot of back pressure. It's really hard because you're basically, by inserting a switch, you're necessarily kind of changing the whole thing. You need to have, however you do it, right? Control plane, this, the data is flowing that. However, if you're replacing something, you know, more trivial, like let's say you're just replacing the laser source or something, then you can do it much more easily. And what's more interesting is you can actually replace the links. So some of the stuff that I showed today, yes, it's advanced, you know, it's very forward-looking, but I didn't mention this, but we also have a company that's building it, and and not just us, there's a few companies out there that are doing this, and so there's a lot of interest in inserting that technology in systems right now. There's a lot of pull into that. honestly, if we could, you know, if we could scale up the manufacturing, you know, we would have buyers for it, so to speak, right? So it depends, you know, there are some technologies that are easier to integrate into systems because it's essentially a plug and play, right? You just replace, you know, there's some packaging, but you just replace what is the current. You don't have to replace the whole software layer as well. But, you know, the exciting thing is if you really make an end-to-end optical system with the switches, with, you know, transparency and all the good things that we want, yeah, that's a much harder sell. I don't know that we can really, I mean, George is probably an exception, but, you know, doing things like that at scale in the universities, you know, I don't know if that's the right place to do it, yeah.
Can I build upon that and ask a question to the panel based on something that I think Karen said, which I found really, that resonated with me. So I didn't come from the optics community. In fact, even today I have very dim memories of how to do an integral. You know, that's not my thing. I did know at one time, but anyways. So one of the things that I found listening to your discussion is that in the SIGCOMM community, the networking community, simulators were very important for developing new ideas. And it was almost the opposite of what you were describing, which is that a brand new grad student or undergrad could quickly get up and running, simulating some sort of small network. And now the simulations were not accurate or they had their own problems, etc. But at least the community kind of agreed upon certain metrics: bandwidth, flow completion time, throughput. There was various things that we could compare things to, apples to apples. And entering this community as kind of an outsider, one of the things I really found was that there's a lot of knowledge about what metrics you want to prioritize based on what seem like sort of battle wounds from previous disastrous projects and things like that. And is there some way to kind of communicate those or to agree about them? Because I think when we talk about the definition, like George said, but then I think what Karen said about, you know, what does practical mean? It doesn't mean can we build it? The answer is always yes, we can. The problem becomes, how do you prioritize? Well, if we build it with this power level, then the port count goes down, or we could do this, but then that. And I feel like a lot of the disagreement about within the community is not so much this will work or not, but rather what is the relative prioritization of various metrics, if that makes sense. I don't know if that makes sense, but that's something I found, and I'd be curious how we kind of flesh that out or come to agreement, or if we don't come to agreement, at least come at it with why we feel that those are important, if that makes sense.
You had an abstraction. Seriously.
Okay,
Because
okay.
the people who did the simulations had an abstraction that everybody agreed to, fundamentally. And
Right.
we don't, Eugene's work is trying to get that abstraction.
But is that the right abstraction people need? Is
It's-
it overly simplified for hardware people?
Because there are optical like simulation software and things, right? But-
Link level,
Okay, okay.
and there are some system level ones, but I don't know if there's one that, I mean, there's definitely ones that put optics in with a standard topology. I don't know if there's.
So how far away are we from being able to print out a bill of goods and figure out the cost and price, et cetera, for a whole system?
I was gonna say the architecture community, so the EDA, electronic design automation. So it's a whole software industry that is simulating everything before they, you know, build out a chip, because it's so expensive. So is there something equivalent to that for, you know, optical network systems, where we could build a fairly accurate, you know, simulator such that, you know, like you were saying, well, what abstraction should we make? I mean, that's a good question, but it is very, so two things. Number one, simulation is nice. Number two, I agree with what Karen has said. There's still some flames out there that, I don't know that the network, that the academic community needs to build something at scale. You know, one or two is already hard enough. And then simulator, so 1, 2, skip a few 9900s, but instead of on earlier. But you would need some simulation, you need some type of realism,
I mean,
for that.
optical systems research, if you submit a paper simulating a system or device to OFC, the will almost certainly get rejected.
Oh, we're trying to change that.
But why is that? Can
I'm
I
trying to
press-
change
let's
that.
press on that. Why is that between Elaine and Dan? Why is that?
I imagine there's different views. Mine is that one is that there's no interesting research involved there, and you need to do the experiment, because you can simulate things to death. If you don't do the experiment, no one will believe it in this community.
These are the scabs left over from like.
That's-
Now, just to put it back, I'm sorry,
Yeah, it
Karen.
doesn't have to be at scale, so I think
Yeah.
that, you know, at OFC and similar places, you know, you will get a high quality paper that has the theoretical or the modeling background, but that demonstrates, you know, the component or the subsystem, and those papers are, you know, all the time. You know.
But to your point, Hakeem, right, those statements are with a technology that they've used for 30 years, and they've had a roadmap that they followed for 30 years, okay? There's at least, 4 or 5 different kinds of material systems, devices built on those material systems. It's much, much more heterogeneous. So there isn't like a single thing or a single roadmap that people necessarily follow. In fact, there's competing technologies now for some of the advanced things, right? I think people don't know, you know, what technology is going to be used for these super high-speed modulators. There's multiple things that people are looking at, and it's kind of we're not sure which one's going to win out. So it's very difficult to design things when you're not even sure what the fundamental device technology is going to be, right? And that happens all the time. There's at least 4 or 5 different platforms that people use.
Can I just also say, with, you know, going back to OFC, what we're trying to do is we're trying to place the right people on the right, you know, track, right? For example, for OFC would be track, and you know, but that's one part. The other part is to communicate that you can't possibly, for example, if I'm doing front hall, right, 6G, I can't build that in my lab. You know, I will have to at some point, you know, harvest the data, yes, experimentally, but simulate it. And so there's a bit of, you know, awareness and knowledge, but also getting the right people to judge the paper, you know, in a fair way. So that's what we're trying to do.
So, if you're a student, I mean, being in one of your labs would be an amazing opportunity. You'd have access to all of this incredible technology, et cetera. But doesn't this create a problem in terms of, broadly speaking, diversity across the community, in the sense that if you don't have access to all of these resources, et cetera, how do you do research? In other words, how do we make it so that labs that don't have heavy amounts of funding are able to contribute to this community?
We see that a lot in post-deadline papers in OFC, right? I mean, you know, and you can see the have and have-nots.
That seems bad though, right?
Yeah, I mean, I'm not
So
arguing.
what are post-deadline papers?
So
Oxymoron,
are you taking a minute? I mean, are you genuinely interested in post?
No, he's not in the OFC community, so he's not.
I'm saying I don't know what it is.
Yeah.
So it is, how do I describe it? It is,
So,
hot
you know, so there's a
off the press.
deadline, right,
Yeah.
where you submit the paper, it gets reviewed, and then, you know, shortly before the conference, like a month before the conference, usually, there's an opportunity to submit, like record-breaking, you know, hot off the press results that, you know, that would merit, you know, quote-unquote, post-deadline, and, like really exciting new results, right? And those are usually some of the most exciting. Some people secretly save their best results for the post-deadline.
Yeah.
It's even more competitive than the regular paper.
It's one of those language type things, it's different
There
communities.
you go.
Right.
Yeah, we probably need to have a glossary in here, right?
Yeah, extra good.
Yeah.
Yeah.
And this is
That's fair.
one of the
Yeah.
importance of going to these
Yeah.
meetings, right? And a lot of people say, well, it's just present your work, you know, what's, but I think really learning all the unspoken, or I should say unwritten things within a community is so important to, if you're gonna publish at OFC in the optical community, you gotta go there, talk to people, learn about post-deadline paper, but learn about also the techniques that people use and what's common practice that almost always is not written in the paper. No one's gonna write a paper that, says this is why you do this or that, because it's just assumed that everyone understands these are how you do it, right?
Yeah, the same could be said for the sitcom community.
I'm learning fast.
Although we do have a very famous how to write a paper by Kesha that I can point you to. Yeah.
They've tried.
And I like the thing that you said about, how do we review sitcom? I think that's a really good knowledge to have, yeah. Mm.
Just going back on the abstraction, layers of abstractions and merging the gap between the systems and the physical layer. I think that one of the challenges, right? Like, you're building hardware, you're building systems, and then come up with some potentially, new photonic architecture. How do you evaluate it, right? I think there's a big missing gap there. And it's always like apples to oranges to whatever, berries. There isn't a so-called ground truth. And, we do a lot, okay, let's compare it to a closed topology, let's compare it to this. And it's always like a bit of a mess, especially in communities like sitcom, where you want to have like a cost function. You want to know, like, okay, this is, it's really hard to do in optics, because a lot of times the technology itself is not really out there. You're not really buying it. You don't have it's hard to put a value on, the cost of a rotor net switch, right? It took N years to build the first one, but maybe the next one will be less expensive, whatever, right? So the heterogeneity of the technologies makes it really difficult. So I think that if we as a community could come up with, like reference models, right? And we have some good examples, right? We have some architectures that have, stood the test of time. I would say Helios is one of them, right? Here's an architecture that stood the test of time that we refer back to a lot. But if you could come up with some references like that, reference systems, it would help a lot in moving the needle and also communicating back to the physical layer people that, okay, a lot of device people that are not in this room, right, that are going to like Clio and OFC and optics conferences, they're making these great technologies, but they don't quite know, which ones would, what to focus on. There's a big design space in the technologies as well. I want to focus on the data rate, I want to focus on the broadbandness, the resilience, whatever. And so being able to communicate back the metrics to the technologies also would be very useful.
Well, I have a question. So from the systems perspective, I mean, like there are some system research, and I want to know from like for device people, how do you see such work? Do you find many assumptions wrong, or is the contribution like partially valid? Like UCSD has this luxury, and you guys have extreme dedication to build this entire system across the stack. But for most researchers, we start from somewhere with some assumptions, okay? But like from the hardware's perspective, how do you view such work? Are they mostly wrong, or you find them irrelevant, or can be partially interesting?
I can give an opinion. I think that when you see a paper that is, it's usually a systems paper, right? It's usually like a point solution. It's like here's an architecture, blah blah blah, X, and it has this technology and it works this way and it's better than what we did before, and great. But there really isn't, in general, I don't want to make specific, but in general, there really isn't, from those kinds of papers, guidance or projections into, hey, if you could make, this is what we did, with, these kinds of switches or these kinds of transceivers. If you could make transceivers that can do, this kind of performance, or switches that can scale to this kind of radix, et cetera, this is the path, right? So we have, the systems papers tend to be like, hey, this is what we did, yay, we're the best, point solution, but with very little roadmap in terms of where guidance for the technologies of where we wanna go. I think if we could have more of that, I think that would strengthen the interactions between the technology people and the systems people, in my opinion. Like today I learned from George that, you know, if we had burst mode transceivers, we could do a lot better for his, you know, but I didn't really know that before, as an example.
But is there a way to really have some like optical devices 101, something like that's more accessible to computer scientists? I find this knowledge is super deep, okay? Like nowhere to start from. For example, the hollow core fibers, I just see them as faster fibers. Like from the system's perspective, like are there anything fundamental?
Oh yeah, there's no dispersion. And so if you understand dispersion, I mean, it's not just that they're lossless. It's that all of the power hungry DSP that you would use to compensate for them, that's out the window. You don't need, I mean, they're
No non-linearity either.
well,
so
very
I think
extremely no
dynamic
nonlinearity,
environment,
almost virtually no dispersion,
yeah.
because all of the light is carried in air, which is very, very dispersionless, and they're low loss. These are huge things, right? The question is, you know, why aren't they there right now? There's just this tiny little issue of, you know, connectorizing, which they're working on like crazy, and
I think they have good solutions for it, but I mean, there's no set research path, and like, so there's the example of the recirculating loop in long distance fiber transmission, right? So we came up with this technique, which actually was an emulation, right? So you took a bank of CW lasers, put them through a couple of modulators, and now you have, you know, 60, 100 signals, right, that you're emulating, and you put those through 4 spans or 6 spans of fiber, and you loop it around, and the community accepted that that emulation of a long distance transmission system was valid if you follow these certain practices, and everyone was off to the races. So then there's a million different variants of how you now get your bits per second per kilometer, or dollars per bits per second per kilometer up, right? And once that path gets established, then it's very clear what the metrics are and the practices are and this sort of thing. But until that gets established, it's kind of everyone's, you know, trying to figure out what to do, how to do it, what makes sense, and this sort of thing. And so a lot of things, like I would say hollow core fiber right now, we don't know what the right metrics are, what the system architecture even needs to look like for these types of systems. It's still very, very new. So you won't get that clarity maybe that a computer scientist would be looking for until much later, right? So.
And it gets back to this whole idea of reference designs, because the traditional networking community has their baseline systems. They're what are deployed. So if you stay within that technology vein, it's a very easy argument to make, because you're taking either established components and rearranging them within that ecosystem and showing new functionalities, or you're just marginally changing, or maybe changing a lot, just one thing, but the metrics and the system level metrics are still established. I mean, getting back to Dan's point, believe it or not, there was a debate years ago on even how to measure bit error rate for optical links, and the reason for that has to do with how long a run of zeros or ones you had to put in there, because you could basically cheat if you put them too short. So there had to be a whole thing on just measuring something as basic as bit error rate. So until we actually have systems like the electronics people do, right, where that whole roadmap is understood, to your point, it is very, very hard. And I think that really has hindered us. Is how do you even show that your system is better, right? Do you have to make up the metric yourself, right? Whereas in other fields, they're pretty well established. But even if you say, well, let's just make up a whole bunch of metrics, that's very, very hard with physical layer technologies that are very, very rapidly evolving, right? Because as soon as we make them up, that metric may be displaced, because the whole ecosystem is very rapidly evolving. So it's just hard.
Did you have something to add?
No, I was gonna go back to your point about, you know, the inequitability in lab equipment and, you know, how rich a lab is and otherwise. I mean, the other thing, and I don't wanna end the panel in such a sad sort of moot point, but the other thing is, you know, I could have an idea and I could, you know, prove, you know, and have proof of concept and have the same results as, you know, another person from a well-established lab, let's say, right? And there could still be bias there in terms of, you know, paper acceptance, in terms of, you know, whether, you know, they believe your results. So even in that case, you know, there is still inequitability there. But at OFC, we're trying to sort of eliminate that and reduce that with double-blind review. Yeah, but like I say, I don't want to end the panel
No,
in a
so
very
I'll ask,
sort of
so
moot
that we
point,
don't
but-
do that, let me just, I'll ask one last kind of rapid fire question and then maybe we can wrap up. So, per international law, I'm required to talk about AI. I just wanna ask, so everyone can agree AI is driving high bandwidths. Everyone can agree that basically dump trucks of money are being spent on AI technology. Do you think the confluence of those 2 points is gonna drive optics and photonics really integrally into the sort of fiber of really deployed networks, or in terms of switching, in terms of endpoint? In other words, is this a renaissance period for the optics community, or do you think that the community will end up relying on more traditional approaches? Take that for what it's worth. Is this like a great opportunity, or is this another bump in the road?
You wanna go in order?
Either way, whatever order you want to go into, maybe. Maybe we'll go the opposite order than we started, so maybe Elaine then George, Dan.
Okay, all right. I mean, there are obviously advantages to applying, you know, AI. I'm thinking Gen AI, controversially, you know, definitely improvements in work efficiencies, but I think we have to get through the mental, but also the behavioral, the acceptance that AI is here to stay. I think AI is here to stay. I mean, it's pervasive in everything we actually do. My 16-year-old is doing machine learning. To your question, whether it is going to revive, I mean, whether we're going to see another, you know, boom, like when I started my PhD, and then when I finished, no jobs.
Hopefully not that.
I'm not too sure, yeah,
Okay.
of that, but yeah.
Okay.
Yeah, so disruption drives innovation. This is the most disruptive time in networking in a generation. So I'm actually, I wish I was 20 years younger. I truly believe, so first of all, people will actually talk to you about your wild ideas. Now they're not thinking they're so crazy anymore because things are being pushed so hard. That's great. So I firmly believe that there's going to be dramatic change. Well, there will have to be dramatic change in how we build networks. Whether or not that dramatic change involves lots of optical technology, I'm very hopeful for. That's kind of where I stand.
Can I throw just a addendum to that? Is it different than like the .com bubble?
Absolutely. Yeah. The .com bubble, okay. .com bubble came because somebody didn't know the little number above the little e meant you really had to get that one right.
Yeah.
Because they were assuming the bandwidth was doubling every 6 months when it was actually doubling. When it was actually doubling every year. You know, what's the big difference in a doubling rate of 6 months?
WorldCom was lying about their numbers.
Yeah, exactly.
But it was a .com followed by a telecom bubble, and maybe a similarity would be that we're seeing this kind of AI, again, software bubble that is likely to be followed by, and we're kind of seeing signs of this hardware bubble because of the software discovers that, oops, I can't do all this stuff without doing something about the network. So, and then I think that's the exciting thing that we're seeing. I mean, for me, so I have a slide that I present where I point out that the network architecture that I've seen for the last, well, my entire career is changing for the first time, right? So we have this DCI network backbone, and now with the mesh network at the edge and this kind of thing, and it's not done changing, right? So there's a number of things still at play there that will be very interesting to see how they fall out. And Meta is just saying that they're actually going back to the future where kind of getting rid of ROADMs and doing everything point to point. I don't know if that's gonna hold out. I mean, a lot of interesting change going on here.
Yeah, I'm very optimistic. I mean, I see it happening, and I think the biggest, in my world, you know, the biggest change has been, the fact that we can get photonics on a chip now, right? So, in a real way, and that wasn't possible back in the early 2000s yet. And so now we can get it on a chip, we can get it co-integrated with the processing and everything else. And, I mean, you know, they're basically, you know, some of the systems vendors are actually coming to ask and asking for. I feel like if the photonic technology was mature enough in terms of the manufacturing and volumes, and I mean the integrated photonics, not the telecom, it would, you know, it would go. It's just that it's a matter of cost, really, and execution right now. So I think in the next 5 years, it's in systems.
Can I just say, you know, the group that I think is missing in this conversation and we must engage are the people from, you know, the mobile wireless, you know, the cellular. I mean, they need us. You know, we're talking about, you know, front hole of, you know, if you look at those antennas, if you look at 6G, it's like 800 gigabits per second. You know, they need optics. We need coherent optics at the PON level. And yeah, so I think we need to get them into the conversation. Yeah.
Okay. Well, we'll leave it on an optimistic, it's time to buy the optics community, so it's on the upswing. So let's thank our panelists. Thank you very much. Back to you.
Okay, thanks everyone for coming. I hope everyone enjoyed today. So the last thing, let's shoot a photo. Yeah, so let's